Hi everyone, welcome. Good evening to one and all present here. Welcome to the sixth weekly live session of the NPTEL course of Remote Sensing Principles and Applications. This is brought to you by NPTEL and the SWAM initiative. I'm Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme from the Interdisciplinary Center for Water Research at IISc Bangalore, and this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. First thing first, the common information. The video recordings of these sessions will be made available to you on the YouTube channel. I've already shared the link of the YouTube channel with you. The files relevant to the sessions will be made available through a Google Drive folder. The Google Drive folder's link is also made available to you already. And so far, all the previous 5 weekly live sessions videos as well as the contents have been already uploaded. The files and the video recordings will be made immediately available after the class. I will make sure to upload them. At max an hour right after the class ends, the weekly live session ends, and the images, if they have been taken from the internet, are solely for study purpose. So these are the videos which I have uploaded on the NPTEL on the YouTube channel. So I've already uploaded the previous 5 weekly live session videos there. So you can go through them and refer to them in case you need to. And this is the Google Drive link where I actually upload the contents. Just a second, someone is trying to enter. So in this weekly live session, we will be exclusively discussing the problems. So I prepared a list of 20 different set of numerical problems. We will be solving them, and it would be only this weekly live session will be only based on numerical problem solving. Nothing based on theory, nothing based on coding, only numerical problem solving. So let's see. The first question is the wavelength of maximum spectral radiant excitance is related to its temperature by A. Is it inversely proportional, or B. Is it directly proportional, C. Is it equal, or D. Is it not related at all? So it is actually related to something called the Wien's law, and the actual answer is inversely proportional. A. I'll just give a brief theory about this question so that we can build up to the later questions. So it's basically about the Wien's law. The three fundamental equations or laws in the in remote sensing which I've learned so far related to this content are: number one, the Stephen Boltzmann law; secondly, the Wien's law; and the third one is the Planck's law. And Planck's law is the basically the origin of the other two laws, of course. So it relates an object's maximum. Oh, sorry. Emitted wavelength of radiation to the object's temperature. Wavelength of the maximum emitted radiation by an object is inversely proportional to the object's absolute temperature. So one very important thing to be noted is that we are dealing with absolute temperatures only, which means that we are dealing with temperatures in Kelvin. So the expression is that the maximum emitted wavelength of the radiation is a constant W or A or whatever constant, I mean whatever I mean term you want to refer to, it is W by T, where lambda max is the wavelength. Let us write it in micrometers. W is the constant, which is 2898 micrometer Kelvin, and T is the temperature in Kelvin. So if you have to find lambda max in terms of micrometers, then you have to put the value of W or the constant in terms of micrometer Kelvin only. Now let's do an activity. Lambda max is 1 by T, so it's inversely proportional. That is why we got to this answer. Anyways, let's do some activity. I will take another slide to do that. Let's apply Wien's law to the sun and earth. So let's first take it for the sun. The lambda max for that case would be 2898 micrometer Kelvin by the absolute temperature of the sun is around 6000 kelvins, by the way. So it would come out to be 0.483 microns. Whereas for earth, lambda max would be again 2898 micrometer Kelvin by so 273 I mean plus, let's take 27 degrees Celsius. Okay, so it would be 2898 Kelvin. So if the average temperature on the earth is let's say 27 degrees Celsius, then it would be 2898 micrometer Kelvin by 300 Kelvin, which would come out to be 9.66 micrometers. So one important thing to be noted is that the sun's maximum wavelength of the radiation, emitted radiation, is actually in the visible range, which is from 0.4 to 0.7 microns. Whereas the Earth's maximum wavelength radiation is in the infrared range. Sun radiates its maximum energy within the visible portion of the radiation spectrum, while Earth radiates its maximum energy in the infrared portion of the spectrum. Okay, so let's take another slide, just a final slide to describe this further. Yes, is there any question? Is there any question from your side? Because you have unmuted yourself.
Sorry, sir.
Okay. So the graph, the plot between the relative radiative energy and the wavelength would look somewhat like this. I'm going to tell you what these entities actually mean. So this peak would happen around 0.5 microns. This peak would be around 1 micron, and this would be around 10 microns. So this is the one for 290 Kelvin. That would be close to the surface temperature of Earth. This would be sorry, what happened? This plot would be for a temperature around 2900 Kelvin, which is that of a halogen lamp, the lamps which you use in your households. And this one, with the shortest wavelength, is that of sun, which is around 5800 Kelvin, and that is of sun. Okay, so and we know very well that the low energy is here. As we move higher, the energy increases. It's pretty evident. So we are done with the first question. We understood what Wien's law is, and then I mean, of course, we tried to have a feel of the maximum wavelength emittance uh, for the sun as well as the Earth. The temperatures are hugely different, so the lambda max would also differ a lot. We understood that the lambda max for sun would be in the visible spectrum itself, whereas for Earth it is in the infrared spectrum. So these are the major takeaways from this question.
सर जो अर्थ और सन की वैल्यूज हैं सर ये लेट्स एज्यूम की गई है या रियल में ऐसी है?
ऐसा ही होता है, ये 5500 से लेके 6500 केल्विन के आसपास लेते हैं। एंड अर्थ का जो टेम्परेचर है दैट इज अराउंड 18 से लेके 25 डिग्री सेल्सियस के आसपास है एवरेज टेम्परेचर एक्चुअली। ठीक है ना?
टेम्परेचर नहीं, ये जो वैल्यू है वेवलेंथ इसकी।
सो अगर तुम इसमें थोड़ा बहुत अगर +-10 20 डिग्री भी कर दोगे ना अर्थ के टेम्परेचर में, इट वुड स्टिल बी इन इंफ्रारेड स्पेक्ट्रम इटसेल्फ। समझे?
कोई खास अंतर नहीं आएगा?
नहीं नहीं आएगा ना, क्योंकि द न्यूमरेटर इज सो ह्यूज, द न्यूमरेटर इज सो ह्यूज।
यस सर।
It would be still in the infrared radiation range itself, spectrum itself. Okay.
यस सर।
Okay. So let's take the second question now. The second question is calculate the total radiance exitance from a black body at a temperature of 298 kelvins. So it's straightforward. It's based on the Stephen Boltzmann law. So let's see the law first of all. Stephen Boltzmann law. As I told you earlier, the three fundamental laws or equations in this part of the remote sensing course are: number one, the Wien's law, which we have already encountered in the first question. The second one is the Stephen Boltzmann law, which we are encountering currently. And the third one is a Planck's law. There would be a question based on Planck's law also. I've set a question which you would find, I think, 2 to 3 questions from now. So, anyways, so Stephen Boltzmann law states that the radiance exitance from a black body is basically sigma times T to the power 4. So BB here is the black body, for which the emissivity is exactly equal to 1. And sigma is the Stephen Boltzmann law constant, which is 5.67 into 10 power minus 8 watts per meter square per Kelvin power 4. And it's actually very easy to remember this constant. It is 5, 6, 7, 8. So all these are consecutive numbers. So it's very easy to memorize this constant at least. Okay, so the temperature is already given in terms of absolute temperature. It is 298 kelvins. So let's find it out. E would be equal to sigma T to the power 4 which is 5.67 into 10 power minus 8 watt per meter square per Kelvin power 4 times 298 Kelvin whole power 4. So you will get the answer as 447.14 watts per meter square. Let's take an additional question. So this would be 298 Kelvin. We know very well is the average temperature of Earth, basically, more or less. So let's take those same cases of the halogen lamp, and as of the halogen lamp, first of all. Okay, I think we have enough space to do it in this, yeah, in this slide itself. Uh, so an additional question would be, what would happen at T is equal to 2727 degrees Celsius. That is usually the average temperature of halogen lamp. So T is 2727 plus 273. You want to convert it into Kelvin. You cannot put the equation is only set if you have to use temperature in terms of Kelvin. So it would be exactly 3000 kelvins. So E is sigma T to the power 4. We are again assuming it to be a black body. That is epsilon equal to 1, equal to 5.67 into 10 power minus 8 into 3000 power 4, and the answer would come out to be 4.952 into 10 per 6 watts per meter square. So we observe here that just by, the temperature, whenever the temperature increases so much, the the total radiance exitance from a black body would change massively. So the it is the temperature, the radiance exitance for Earth was around 4.47 into 10 power 2 watts per meter square. It is it is basically 10 power 4 times more, in very rough terms, when we are when the temperature is rising by this much. Okay, so let's take the third question now. And if there is any question, please feel free to interrupt me and shoot your question straight away. No issues with that. Anyway, so we are moving into the third question. Assuming the sun is approximately a 5700 Kelvin blackbody radiator with a diameter of 1,392,000 kilometers, what is A, the wavelength of maximum spectral radiant excitance, B, the spectral radiant excitance at its wavelength, and C, the total radiant excitance from the sun, and D, the total power output of the sun? So this question would require you to have a knowledge of the Planck's law. So in the first question we solved it using the Wien's displacement law. Second question actually followed the concepts of the Stephen Boltzmann law, and the third one would introduce you uh, to the Planck's law, which is the most fundamental law in this remote sensing course. So part A wants you to know the wavelength of maximum spectral radiant excitance. Okay, so this is straightforward, or peak. This is straightforward. This is just the this part A is just the Wien's displacement law. We did it just like two questions from now. So it is 2898 micrometer Kelvin by temperature. Temperature is 5700 kelvins, already given in the question. So it comes out to be 0.508 micrometer, again in the visible range. So question number B, what does it ask you? The spectral radiant excitance at this wavelength. Okay. Spectral radiant excitance at this wavelength. And if you want to know how these three laws are related, how Stephen Boltzmann law, Wien's displacement law, and Planck's law related, you can refer to. I mean, if I'm not wrong, the video recordings of weekly live session 2. I have actually derived it in that weekly live session. In case you are interested in the derivation part. So for this part, we would be required to understand or use the Planck's law. So the Planck's law is m lambda comma t, that is the radiant exitance for a particular wavelength lambda and a particular absolute temperature T. It comes out to be 2 pi hc square by lambda power 5 exponent hc by lambda kt minus 1. So this is the Planck's law. We know it very well. It has been already referred to also, but yeah, I will be taking another slide. So we need to find out the radiant exitance for that same temperature and for that same wavelength. So the wavelength which we found out from that previous question was 0.508 micrometers and the temperature was 5700 Kelvin. So this is 0.508 and temperature is 5700 Kelvin. So we have just put the value. Just put the value in this expression, and you will get the result. It's as simple as that. So let's write 2 pi is a constant. Let's take it out for the time being. H is the Planck's constant, 6.6 into 10 power minus 34 joules second, into c we know is the speed of light. It is 3 into 10 power 8 meter per second, and there was c square, so we have to square this term, by lambda we found out as 0.508 microns. So 0.508 convert into meters into 10 power minus 6, and it is lambda to the power 5, so power of 5 to it. Then this exponential term, exponent hc by lambda kt. H is, we know very well, is the Planck's constant, 6.6 into 10 power minus 34 joules second, into 3 into 10 power 8 meter per second, by lambda kt. Lambda again comes here, so lambda is 5.508 into 10 power minus 6 meters. K is the Boltzmann constant, is 1.38 into 10 power minus 23 joules per Kelvin times T. T we have to put in absolute terms, so it is 5700 Kelvin minus 1. So this is the expression. So it would come out to be 3.732 into 10 power minus 16 joules meter square per second by 0.508 into 10 power minus 6 power 5 exponential 1.98 into 10 power minus 25 joules meter by 3.99 into 10 power minus 26 joules meter. So the units get cancelled out. According to dimensional analysis, it is absolutely right so far. It would come out to be 3.732 into 10 power minus 16 joules meter square per second by 0.508 into 10 power minus 6 power 5. This would be meter power 5 times this entity comes out to be 140.89. So finally we get 3.732 into 10 power minus 16 joules meter square per second by 4.766 into 10 power minus 30 meter to the power 5. Let's take another slide to finish this question, this part of the question actually. So the final answer comes out to be 7.83 into 10 to power 13 joules per second per meter cube. Now we know that 1 watt equal to 1 joules per second. We know that very well. So 7.83 into 10 power 7, because we are converting the meter into micrometer. Okay, so it would come out to be watts per meter square per micrometer, and that would be the answer. So the third part of the question was the total radiant exitance from the sun. So the total radiant exitance. So how would we find it? It's very straightforward. It's the Stephen Boltzmann law. So this question actually wants you to be thorough with all the three laws of this remote sensing course. So the third question asks you about the knowledge of Stephen Boltzmann law. Total radiant exitance of the sun. So m total, we know it would be sigma times sigma, epsilon times sigma t to the power 4, where epsilon is the emissivity and epsilon equal to 1 for sun. It's almost 0.99, 0.995. It's very huge actually. So it's almost 1 for sun. So we can, so it is 1. So it is just sigma t to the power 4. 5.67 into 10 power minus 8 watts per meter square per Kelvin power 4. T to power 4 is times 5700 Kelvin power 4, which comes out to be 5.98 into 10 power 7 watts per meter square. Okay, so this is the third part of the question. The fourth part is the total power output of the sun. Total power output of the sun. Let's do it here. Another slide I would require. Total power output of the sun. What is that exactly? So total power. So far we got answers in watts per meter square. You just need to multiply it with the surface area. It's as simple as that. So it is m total, which we found out from the previous question, times the A of the sun, the surface area of the sun. So m total, the surface area of the sun would be 4 pi r square of the sun. So it comes out to be 5.98 into 10 power 7. It was already what we found out in the previous part of this question, times 4 times pi into r square. R would be diameter by 2. Diameter is 1.392 millions square kilometers. So let's do that. 392 into 10 power 9 by 2 meter whole square. So into 4 pi. Oh, sorry, this is the third question. Yeah, 4 pi into 1.392 was a dia, into 10 power 9 meter. When we compare kilometer into meter, by 2. So this would be the radius and square it. So we get it as 3.64 into 10 to the power 26 watts. So it's a huge number, the total power output of the sun. Now let's move to the next question. But if you have any doubt, please feel free to interrupt me and ask me. Anyways, we are going to solve 20 questions today, so we would try to be a bit faster. The next question is that if you have a source at a temperature of 1000 Kelvin and an emissivity of 0.93, what is the radiant exitance of the source? Okay, so it's very straightforward, right? So it is emissivity. It has something to do with the Stephen Boltzmann law. It's as simple as that. So emissivity is 0.93, which is basically the radiant excitance of the body by radiant excitance of a black body. Okay, so it needs you to answer what is the radiant excitance of the source. So it is uh, radiant excitance of a black body at a given temperature times the epsilon, which is the emissivity. So it's straightforward. So it would come out to be sigma t to the power 4 times epsilon. So it comes out to be m at T is equal to 1000 Kelvin would come out to be 5.67 into 10 power minus 8 watt per meter square per Kelvin power 4. This term multiplied by temperature is 1000 Kelvin power 4 times the emissivity, which is 0.93. So this comes out to be 52727 watts per meter square. Okay, so let's move to the next question now. Suppose your night study lamp has a radiant flux of 10 watts. What is the irradiance on your radiometry notes which fell 2 meters from the lamp when you fell asleep? Assuming your notes were perpendicular to the night study lamp. Okay, so it's again a very straightforward question, by the way. For I mean, these questions basically are from second and third week of this course. By the way, I mean the very initial weeks where Sir covered the concepts of radiometry in detail. We don't know the area of the nodes, but can propagate the flux out to the surface of a sphere of radius 2 meters. We know very well, I mean, we assume that it is a sphere where, I mean, where we are actually facing it. The sphere radius in this case is 2 meters. The hypothesis, the hypothetical sphere's radius is around 2 meters here. Okay, so sphere would be del phi s by del a. It is 10 watts by the surface area 4 pi r square. 10 watts by 4 pi times 2 meters square. It comes out to be 0.199 watts per meter square. It's very straightforward. Now next question, given the same 10 watts, I mean this question is in continuation to the previous question, by the way. Given the same 10 watt source above, what is the flux on your notes if you are using a standard sheet of paper measuring 8.5 inch by 11 inch and are 2 meters away, still perpendicular to the night light? Additionally, what is the flux if the notes are tilted 25 degrees? So first of all, we need to change the area in the first part, and in the second one the orientation is also tilted, changed. So we need to do these two modifications to the previous question. So the funda is that we subtend a section of the sphere with the area of the paper. So we need to change the area. At this point, the irradiance onto the paper, which we refer as e-paper, is the same as the, so same concept basically which we used in the last question, irradiance on the surface of the sphere. that is E sphere of a radius R. So E paper, in this case we are subtending the sphere into the paper, by the way. So it is del phi paper, again the same thing, by del A paper. So we need to find out the what is the flux. The flux we need to know, need to find. So del phi paper would be E sphere times del A paper. We just need to change the area. So E sphere 0.199 watts per meter square, which is what we found out from the previous question. 0.199 watts per meter square times area of the paper. Area of the paper is 8.5 inch by 11 inch. So we will take another slide. Del phi paper would be 0.199 watts per meter square times, just multiply the area and convert it into meters, the SI unit, 603 meter square, since 1 inch is 0.0254 meters. So from here you get del phi paper equal to 12 milliwatts. The answer you get is in watts. You just divide it with 10 power minus 3, you get in milliwatts. Now the second part of the question is that what would happen if you tilt if the notes, if you tilt the notes by 25 degree, what would happen? I will take another slide just to explain it. So if the notes are tilted uh, by 25 degrees, we have to account for the projected area in many cases of radiometry the angle is zero, but that is not the case in this question. That is paper is not tilted in many cases, as the one which you saw just now. So for those cases cos 0 degree is 1, so there is no correction at all, but in this case you need to take into account the tilt correction. It would be del phi paper times cos theta. Cos 0 degree, it is not 0 degree anymore, it is actually 25 degree. So from the previous question it was 0.012 watts was what the del phi which we found out. So 12 milliwatts is nothing but 0.012 watts times cos 25 degree, because the tilt as given in the question is 25 degrees. So you find it out as 10.9 milliwatts. So if you are tilting it, it is actually, the flux is actually decreasing. It's common sense again. Now let's move to the seventh question of today. Your headlights have a radiant intensity of 60 watts per steradian. Determine the irradiance on a signpost which is 2 meters away. Okay. So this requires you to use the fundamentals of the inverse square law. The farther the distance is, the inversely it will decrease with respect to the distance. So inverse square law You have already seen it in the week second and third of this course, by the way. Intensity of radiation is inversely proportional to the square of the distance. So let us suppose this is the source. The source strength is, let us suppose, S. You assume a hypothetical sphere around it. Let's suppose this is the hypothetical sphere. Uh, the intensity goes on like this. Okay, so intensity at the surface, let us of this hypothetical sphere at surface of sphere is equal to I is source strength by 4 pi r square. So it follows that for a point source, as distance increases, intensity decreases, or I is 1 by d to power 2 d to power 2, where d is the distance and I is the radiation intensity. Okay, so let's use the funda here to come to it. But there is a caveat to this case also. We need to ensure that the size, the dimensions of the source are much smaller than the distance we are propagating it to. So that caveat comes in. I will write it down in the next slide. So you cannot blindly use it, use this formula. You can blindly use it probably for this course, because for this course the size of the source does not matter. I mean, it's not something which is extensively covered, but you need to check it. You need to check it at least once, whether the size of the source is almost of the same magnitude as the distance. But let's check it. So we can use the inverse square law as long as our distance from the source is at least 10 times greater than the diameter of the source. So there's a caveat to this. So or in simpler terms, that is, distance by dia should be at least greater than 10. That is the caveat of the usage of this formula, by the way. You cannot use it blindly. Okay, so let's see what happens for this problem. For this problem, the diameter of the source can be no larger than, dia should be less than distance by 10, that is less than 2 meter by 10, which is equal to 20 centimeter. Now luckily, I mean, 20 centimeter is actually a little larger than a typical headlight. This question actually asks you about headlights. So this is little larger than the dia of typical headlights. So we are lucky. We can use this equation. Straightforward. Greater than a typical headlight. So let's solve this then. Uh, so E is equal to I by R square, which comes out to be 60 watts per steradian by 15 watts per meter square. So that's the storyline. Next question, why do dark objects get hot in direct sunlight even though a lot of sun's infrared radiation does not get through the atmosphere? That is a very interesting question, and this question is actually conceptual. So dark objects are actually good at absorbing all the types of electromagnetic radiation waves, and they will also re-emit them as infrared radiation. So that is the reason. Dark objects are good at absorbing all types of electromagnetic waves and will re-emit them as infrared radiation, which we call as the long wave radiation. Okay. Now water vapor is a strong absorber of the infrared radiation, which is why the temperature suddenly drops when the sun is hidden by a cloud. We feel much colder during that time. I mean, whenever let us suppose it's a winter, on a sunny winter day versus a cloudy winter day, you would feel much more uncomfortable during a cloudy winter day. And also, why infrared detecting telescopes are at high altitudes at space. We cannot keep it in ground because it will actually capture the re-emitted infrared radiation from the surface or from the dark surface. So that is why these sensors are kept much higher in the space. The next question is again on similar concepts. The separation between the screen and a plane mirror is 2R. An isotropic point source of light is placed exactly midway between the mirror and the point source. Mirror has a radius of curvature r. Radius of curvature r reflects 100 percentage of the incident light. Then the ratio of illuminances on the screen with and without the mirror is, okay. The funda is like this. There is a screen. So let us suppose this is the isotropic point source. Let's call it a lamp. Okay. And there is a mirror. So this is the mirror. Separation between the screen and a plane mirror is 2R. So this is 2r. Okay, so this is radius of curvature r. So this is again r. So this is a plane mirror. So an image of the source will also be created, and the image distance, since it's a plane mirror with radius of curvature r, so a plane mirror, so it will also be at a distance r actually. So this is a screen, this is a lamp or light source, this is a mirror, and this is the image. So let's see the illuminance on the screen without the mirror is straightforward. It is I1 is equal to the radiance by r square. That is the distance between them, r. This distance I'm talking about. And illuminance with mirror on the screen, it is, let us suppose I2, it is L by r square from the original lamp and from the image also. So that would be plus L by 3r square, because the image distance on the screen is 2r plus r, that is 3r square. So 3r, so we are squaring it basically. So that comes out to be 10 by 9 L by r square. So we need to find out the ratio. I2 by I1 is equal to 10 by 9 L by r square by L by r square. It is 10 by 9 equal to 10 is to 9. That is the ratio. Now, some very small questions just to understand how satellites propagate or orbit around the Earth. I think there would be a list of 5 questions to understand this. The first question is that a satellite at an altitude of 500 kilometer above the surface orbits Earth from pole to pole once every 90 minutes. How many times does it pass across the equator? So this is Earth. Let us suppose this is North Pole NP. This is South Pole, and this is how the satellite is moving. So how many times will it cross the equator per one orbit? Any idea? Would you like to answer? Okay, so since in one orbit it is moving entirely across the Earth, so in one propagation, let us suppose it's moving from uh, North Pole to South Pole, it will encounter the equator once. Then again, when it move from South Pole to North Pole, it will encounter the equator again. So in one orbit, it will pass through the equator twice. It will cross the equator exactly twice per orbit. The next question is if the satellite passes across the equator going north to south uh, during the first half of its orbit, what direction does it pass along the equator during the second part of the orbit? So it's basically pretty. I mean, it's common sense. In the second half of the orbit, it will move from south to north because the first half was basically from north to south. The satellite will travel south to north across the equator during the second half of the orbit. It's pretty straightforward. Then question number 12. How many times does the satellite pass over the equator every day if one day is 24 hours? So in 90 minutes it is completing an orbit. Okay. So number of orbits would be 24 hours if one orbit finishes in 90 minutes. So 90 minutes is nothing but 1.5 hours, which is 16 orbits. So it will finish 16 orbits per day. But they are not asking the number of orbits the satellite is finishing per day. They are actually asking how many times does the satellite pass over the equator every day. We know very well that per orbit it is passing over the equator twice. We did it in question number 10. So per 16 orbits it will pass over the equator 16 times 2, that is 32 times. During each orbit it passes across the equator twice. So in each day it passes the equator two times per orbit. So it would be 2 times 16 orbits, that is 32 times. Next question, if the satellite can view a swath of Earth's surface that is 2500 kilometer wide, how many orbits will it take to view all of the equatorial areas of Earth if the radius of the Earth is 6378 kilometers? Okay, it's a very interesting question, by the way. So we know that it is moving around it is basically observing the circumference of the Earth, the entire circumference of the Earth when it moves across the orbit. So circumference of the Earth is 2 pi r, which is 2 pi or c is equal to 2 pi circumference times r. 6378 kilometers is the radius of the Earth, which comes out to be 40,066 kilometer, 40,066 kilometers. Now number of swaths would be the total circumference by the Earth's surface, which is 2500 kilometers wide. So 2500 kilometers, which will come out to be nearly 16 number of swaths it can do. But each orbit counts for 2 equatorial swaths, which we found out in the previous question. So we need only 8 orbits to provide 16, because per orbit there are 2 equatorial swaths. 16 swaths at the equator. So this will cover all of the equatorial area within the swath images. When the swath images are placed exactly side by side. all of the equatorial area when the swath images are placed exactly side by side. Okay, let's take the next question. Estimate the full swath viewing angle for a satellite orbiting at an altitude 500 kilometer and viewing a swath of 2500 kilometers. So it's very straightforward, by the way. Let us suppose this is a sensor. Let's project a right angle triangle kind of like this. So this would be the entire swath. The swath is 2500 kilometers. What happened? Someone is trying to enter. Let us suppose this angle of the, the half angle is theta, and the altitude is already given to be 500 kilometers. Okay, so tan theta would be 2500 kilometer by 2, which is 1250 kilometer by the altitude, which is 500, which comes out to be 2.5. So this implies theta equal to 68 degree. The inverse of tan 2.5, tan inverse 2.5 is 68 degree. This implies full swath viewing angle is actually 2 theta, because we are concerned about this. This is 2 theta. So it is 2 into 68 degree, which comes out to be 136 degrees. The next question is the distance to the horizon of a planet is given by the formula d is equal to square root of 2 rh. D is equal to square root of 2 RH. Okay, where R is the planet's radius in kilometer and H is the height of the satellite above the ground in kilometers. For the satellite problem above, what is the maximum swath width that can be viewed by the satellite? So, distance to horizon of a planet is, let us suppose it's D. It is given as 2 square root of 2 RH. I will be deriving it in just a few moments from now. But they have already given you the equation, the formula for it. So D is square root 2 R is a planet's radius 6378 kilometers, and H is the height, right, of the satellite. So it comes out to be 500 kilometers. So it comes out as 2525 kilometers. Or let me just take another slide to explain it. So it is 2525 kilometer. And it is almost equal to the total the swath of the Earth's surface, which is 2500 kilometer, which we found from question number 13. So it's almost equal, by the way. It's just a coincidence, but yeah, it's almost equal. Or it is the way these satellites orbits are actually designed. So we get that swath width is almost equal to the maximum area of earth that can be viewed. So it is 2500 kilometers and 2525 kilometers. It's not much different. Viewed from horizon to horizon at the altitude of the satellite. So now let's take a moment to understand what this horizon thing is, maximum distance to horizon thing is. Okay. Uh, how far away is the horizon for a viewer on the Earth? Okay, so we just assume that the Earth is a perfect sphere, which is not the case, but we are just assuming it for the sake of the problem. This is the center of the Earth. The radius is same. Let us subtend a tangent to it. Okay, so the tangent and this, when we extend it, it will meet here. So this is the tangent to the radius. They always form a right angle. I mean, they are always perpendicular to each other. That we know very well. So let this be the h, the height of the observer, and let this is L, and let this thing, the arc length is S. Okay. Assume super simplified. I mean, disclaimer, it is super simplified, that the Earth is a sphere with radius r. Then the line from our eye to the horizon is almost tangent to the circle of radius r. Representing the radius of Earth as shown in the figure. This is what I'm referring to. Now let's understand the notations. Let me make it just once again, just for so that we don't have any doubt. Yes. So this is R, this is R, this is H, this is L, and this is S. Okay. H is the height of our eye level. In the problem, it was the height or the altitude of the satellite. Okay, but in this case, I'm taking the height of the eye level. I mean, just to explain what the horizon means. Above the sea level, R is the radius of Earth. L is small l is the length of line connecting our eye directly to the horizon. S is the arc length. Theta is the angle between our position, which is this one. This is 90 minus theta. So this is theta and the horizon. Okay. So let's use, I mean, this is a right angle triangle, definitely. So let's use the Pythagoras theorem. So L would come out to be R plus H square minus, which is a which is a hypotenuse, minus R square. Okay. So this comes out to be 2RH plus H square. Now we can assume that L is almost equal to the S, as H is very less than R. This implies S nearly equal to L is square root of 2RH plus H square, or equal to square root of 2RH, because H square would be much smaller than 2RH, or it is actually equal to K times square root of H, where K is a constant. Okay, so we are done with it. So we in the last question we had this term, we use this term d equal to square root of 2RH. We have derived it now. So just see this term we used for the last question, we have derived it for this part. So just to have a feeling where it actually arrived from. Now let's take another interesting question, a very interesting one indeed. Question number 16. Two layers of cloud are present above the surface of a planet. The top cloud layer has a surface of 250 Kelvin, temperature of 250 Kelvin, and an emissivity epsilon equal to 0.25. And the lower cloud layer has a temperature of 280 Kelvin and an emissivity epsilon equal to 0.8. How much long wave radiation does the planet's surface receive from the clouds? Very interesting question. So let us suppose this is the surface of the planet. This is the first cloud layer, cloud number one. Let us suppose write it as cloud number one. This is the second cloud layer. This is cloud number two. Let us say cloud number two is T is 250 Kelvin. Emissivity is 0.25. This is T is 280 Kelvin. Emissivity is 0.8. Okay. So we have to find out the emissivity here. So E total, it would be contributed by each of the cloud, by the way. So one of them would be emitted, one of them would be transmitted and then emitted. So let's see. So it's basically emission from bottom cloud plus transmission through bottom cloud from top cloud. Okay, let's see it then. E total is sigma into epsilon. Epsilon is the emissivity. Sigma is the Stephen Boltzmann law constant, 5.67 10 to the power minus 8 times t to the power 4. It would be 0.8 times sigma times 280 power 4 plus 0.2, which is the transmission, 1 minus the emissivity. Okay, so it's a transmission from the bottom cloud into the top cloud times the emissivity of the top cloud times the temperature of the top cloud to the power 4. It's as simple as that. Now epsilon, let's take, suppose we take epsilon as 0.8 of the Earth's surface. We're just assuming that the Earth's surface epsilon is, the emissivity is 0.8. However, there's a disclaimer to it. So Earth's surface emissivity, it varies with respect to the surface features. Usually epsilon is less than 0.85 for deserts and semi-arid areas. Okay, and epsilon is in general in excess of 0.95. It's almost equal to 1, by the way, for vegetation. So we are assuming an epsilon of 0.8. We are assuming that it's a dry area, the surface. Okay, so we are assuming epsilon equal to 0.8. So t to the power 4, when you put the values in this equation, would be 0.8 times 280 power 4, because the sigmas will get cancelled out already, plus 0.2 plus into 0.25 times 250 power 4 by 0.8. So when you solve it, T comes out to be around 282.74 Kelvin. Yes. So we have solved this question also. Let's move to the question number 17th. Assuming the sun to be a spherical body of radius r at a temperature of T Kelvin, evaluate the intensity of radiant power incident on Earth at a distance r from the sun, where r0 is the radius of the Earth and sigma is Stephen's constant. So total power radiated by sun, just a second. Let me check whether it's getting recorded or not. Yes, it's getting recorded. Will be equal to sigma epsilon sigma t to the power 4 times 4 pi r square, but epsilon is equal to 1, nearly equal to 1 for the sun. The emissivity for sun is almost around 0.995. It's almost equal to 1. So let's take it as 1 itself. So this would be equal to sigma t to the power 4 times 4 pi r square. So intensity of power at Earth's surface, you have to use the inverse square law. It's as simple as that, is equal to sigma t to the power 4 into 4 pi r square by 4 pi small r square. Okay, because Earth and Sun are at a distance of small r. So it will come out to be sigma t to the power 4 capital R square by small r square. And that's the answer. So 17th question is done. We will have 3 more questions for the day. The next question is the okay, someone is trying to enter. the Earth receives at its surface radiation from the sun at the rate of at its surface radiation from the sun at the rate of 1400 watts per meter square. The distance of the center of the sun from the surface of the Earth is 1.5 into 10 power 11 meters, and the radius of the sun is 7 into 10 power 8 meters. Treating the sun as a black body, what would be its surface temperature? Okay, the Earth receives the surface radiation from the sun, so that is given. Distance is also given. So we can easily, understand that we need to use some sort of the inverse square formulation to understand the surface temperature. Let's take it. Let's assume that capital R is the radius of sun, d is the distance of the Earth from the center of the sun. So the power radiated by the sun is sigma 8 times t to the power 4. Epsilon is equal to 1 for the sun, as we used in the previous question. So I'm not even writing epsilon for the time being. It would be actually epsilon, and epsilon is equal to 1. So we don't even need to write epsilon, and this would be equal to sigma a is 4 pi r square times t to the power 4. So this power would radiate over a spherical surface, a hypothetical spherical surface. Radiates out over a spherical surface. It's an imaginary spherical surface. Okay. Let's take another slide to just finish it up. Consider a sphere with a radius, it's an imaginary sphere, equal to distance between the sun and the Earth. Let's consider that with center of sun. Okay, so this implies power per unit area, which we term as intensity, at location of Earth's surface would come out to be equal to sigma times 4 pi r square t to the power 4, which we already found out in the previous expression, divided by the, now use the inverse square law, so it's 4 pi d square, the distance, and this is 1400 watts per meter square, right? This is clearly given, indicated in the question, so I'm just equating it to 1400 watts per meter square. Now from it, the only unknown is the temperature T. Let's find it out then. So T to the power 4 is equal to 1400 into d square by sigma r square. This implies T is equal to 1400 into 1.5 into 10 power 11 whole square by 5.68 into 10 power minus 8, 7 into 10 power 8 square, power 1 by 4, and it comes out to be 5801 Kelvin. Okay. Now we are just left with two more questions for the day, but if there is any question, please feel free to ask me. Okay. So we are done with 18 questions already. We will finish today's weekly live session with two more questions. Please give me a break of 1 minute. So this question states that the radiation emitted by a star A is 10,000 times than that of the sun. If the surface temperature of the sun and the star A are 6000 kelvins and 2000 kelvins respectively, then the ratio of the radii of the star A and the sun is okay. So what's given is, I mean, we know that we have to use this fundamental equation. E is equal to sigma epsilon A t to the power 4, and E star is given as 10,000 times E sun. T star, let's denote it as T1. Okay. R star, let's denote it as R1. Okay. T sun is 6000 Kelvin and it is 2000 Kelvin T sun. Okay. And R sun, let it be R2. So E star by E sun is R1 square, just inverse square law, times T1 power 4 by T to the power 4. Okay, let's take another slide just to explain that. This implies 10,000 times E sun, which was E star, by E sun is equal to R1 square by R2 square times T to power 4 by, T1 power 4 times T to power 4 by divided by T to power 4. So it's okay, of the star to that of the sun. So finally we get R1 by R2 to be nearly equal to 900. Now let's take the final question of the day. Of the radiant energy 350 watts per meter square incident upon a surface, 250 watts per meter square is absorbed, 60 watts per meter square is reflected, and the remaining is transmitted through the surface. What is the transmissivity of the surface? Okay, let us suppose it's a water body or anything like that. There is this incoming radiation. It may either be transmitted, which is ET, it may be absorbed, which is EA, or it may be reflected back, which is ER. So EI would be summing up of all the other radiations. So it is ER plus EA plus ET. Now do one thing, divide all of them by EI. So 1 equal to ER by EI plus EA by EI plus ET by EI. So ER by EI is the reflectance, EA by EI is the absorptance, and ET by EI is the transmittance. So what do we get out of it? Reflectance plus absorptance plus transmittance. Okay. So radiant. The question states that of the radiant energy 350 watts per meter square uh, incident upon the surface. So EI is given. EI is 350 watts per meter square. Upon a surface, 250 watts per meter square is absorbed. So EA is 250 watts per meter square. 60 watts per meter square is reflected. ER is 60. Watts per meter square is reflected. Remainder is transmitted. ET we don't know. What is the transmissivity? That is what they want to know. So you just use this equation. So 1 equal to, or you just sum them up. So transmissivity. Let's. I will try another slide. So the transmissivity comes out to be 350, which was incident, minus 250, which was absorbed, plus 60, which is reflected. So whatever rest would be the transmitted part, by 350, which is 350 minus 310 by 350, which is 40 watts per meter square by 350 watts per meter square. So 40 watts per meter square would be transmitted, but the transmissivity would be by dividing it by the incident energy itself. It would come out to be 0.1142 transmissivity, or tau. So with this, we are done for the day. We actually solved 20 distinct type of questions, and we learnt a lot. Primarily, it was on the application of Planck's law in one of the question, and the Wien's displacement law, and also the Stephen Boltzmann law. So we are done for the day. I will be immediately uploading it on the YouTube channel for a reference, as well as uploading the contents on the YouTube channel. So please feel free to refer to that. So let's meet in the next. We are actually halfway into the course already. This is the sixth weekly live session out of the possible 12 of them. So we are halfway to the weekly live sessions already. So in the next week, again on Friday from 6 to 8, I will come up again with the seventh weekly live session. So thanks for joining me. I will stop recording now.